Part 2. We are looking at calculus equations from the math equation sheet. We worked through 6 of the 10 equations last time from the older, simpler sheet. We even looked at one example of the chain rule. More on that in this video as we answer the question, where did all these a's come from? What are they doing? And what can you do about it? Derivatives and integrals as inverse operations, the power series, and e to the x as its own derivative. But what happens when you take e to the ax? It looks like you gain an e, or you lose one. But why? We will take a look at those graphs in just a minute. First, let's destroy something. This function. Let's take the derivative. Got it? Now let's take the derivative of the derivative, f double prime. The same power rule gives the third order derivative, and the fourth and the fifth derivative kills the function, but it shall rise again. We will undo our aggression through integration. But wait a minute, that won't work. We can't find the area under this curve. It's just it's zero. It's nothing, and you can't look at the equation. That's not going to work. We do not have an x to the n. We don't even have x to the 0. All we have is absolutely nothing at all. But wait a minute, we know one thing. We know that the slope of the integral is equal to 0. So really, it could be any of these lines. And we'll need some help to figure out which one. But if all we're looking for is a line with 0 slope, it could be any of these. And this, believe it or not, is a real practical matter for this class. Here's the question. Can you have a voltage where the electric field is 0? Look at those equations. They're kind of scary, I guess. But V stands for voltage. E stands for electric field. X or R are two ways of talking about displacement. Can you guess? You can have a voltage even where the electric field is 0. You just can't have a change in voltage with no electric field. Anyway, this is tough stuff. Anyway, moving on. What's the integral of this line? Y equals 2. Well, use the formula. The integral is y equals 2x. Or is it? Again, we were looking for a line with slope equals 2. And any of these lines will work. And oh no, you know what this means. We're going to have to, I was trying not to do this, but I think we're going to have to use the dreaded 2x plus c. Because all these lines have a slope of 2, so the answer is to the integral is 2x plus c. Now, personally, no one asked me, but personally, I do not like this notation. I think it's a little messy. But you could take any of these indefinite integrals, no bounds on these integrals, and you could rewrite them. Boo. And moving on to the integral of x squared. It could be 1/3 x cubed. We'll ignore the c's after I mentioned that. We're just going to ignore them now because I want to. And the integral of that is 1/12 x to the 4th. The first curve we had so long ago, that's the curve we killed through differentiation. But this curve is immortal because it is its own derivative, the immortal slope. Nice. But what about this? Instead of e to the 1x, let's graph e to the 1/2 x. It's still a curve, but it's less steep. We could say that the derivative is 1/2 the value of the function everywhere. Or we could take e to the 2x. The slope is 2e to the 2x. Do you see what we're doing here? We're keeping the same exponent and pulling out the derivative. You could call this the chain rule and see it at work here with e to the x squared. That's really hard. Oh, that look. No, not really. Slope is e to the x squared times 2x. Again, the same exponent because e gives you the same exponent and its derivative. The chain rule. So much for the exponential function. On to the natural logarithm, the inverse operation. Squeeze the graph of e to the x onto a new axis with the natural logarithm. Back together again, guys. Still the inverse operation. Here are the equations from the old equation sheet, and here they are with the a's. But, especially on that top equation, isn't there an a missing? It seems like we're missing an a. Does anyone else feel like we're missing an a on the top equation? Let's find out what these graphs look like. We will graph e to the x and ln x, or how about e to the 1/2 x and ln 1/2 x, or how about e to the 2x and ln 2x? Did you see what happened? Did you see what didn't happen? E to the x changed its shape. We knew that. Ln x did not change its shape. Isn't that surprising? I was surprised, constantly surprised by this stuff. Anyway, ln x did not change. That's what the equation says, that ln x does not change its derivative, does not change its slope. Could you say it does not change its shape? It is translated up and down. Now, grab the equation, hold it, flip it around, integrate it, inverse operation, so we can say that. Good. And there's the new equation, but that's not what it looks like when you look at it on the equation sheet. This is what it looks like. And I don't like it, but nobody asked me. So let's take a look at what the graphs look like. And in this case, again, plus a, it's a translation. It translates the function left and right. Ln x, it's the very same shape all the time, and we have a way of translating it up and down and left and right. So we have the immortal slope and the indestructible shape working as a team. The A team with the power function and the chain rule. Goodness, if we could get sine and cosine into this party, would be looking good. And that's part 3.